Hello, this is Andrea Hendricks, and I'm going to spend a few moments talking with you about how to graph rational functions. We're going to look at three basic types of rational functions: those that have horizontal asymptotes, those that have holes in the graph, and those that have slant asymptotes. We're going to use a similar process to graph all of these. We're going to begin by finding where the vertical asymptotes or holes occur, where there are horizontal asymptotes or other types of asymptotes, finding the zeros of the function, which you'll recall are the x-intercepts of the graph, finding the y-intercept, and then a few additional points as we need to get a complete picture of the graph. And then lastly, we'll finish up by finding the domain and range of the function. So let's get started with an example where we want to graph this rational function f of x is equal to the quantity 1 minus 2x all over x. So I have an outline for you really to follow. We're going to find the vertical asymptotes, horizontal asymptotes, zeros, y-intercept, something that may be new to you. We're going to look at does a graph cross the horizontal asymptote, a few other points as we need, and then we'll end up with sketching the graph and finding the domain and range. So, as far as the vertical asymptotes go, recall those come from where the denominator of the function is equal to 0. So simply here we would set the quantity x equal to 0. And that's already solved for us. We know that this is not a hole because there's not a factor of x in the numerator that this will reduce with. So we have a vertical asymptote at 0. Our horizontal asymptote, you'll recall, comes from the relationship with the degrees of the numerator and denominator. In this case, we have the same degree between the numerator and denominator, so our horizontal asymptote is the ratio of those leading coefficients. So we would have y is equal to, the leading coefficient in the numerator is negative 2, divided by the coefficient of x in the denominator is 1. So we have a horizontal asymptote at negative 2. Now, what about our zeros? Zeros come from where that rational function is equal to 0, and you might recall that whenever you have a fraction, the only way for it to be equal to 0 is if the numerator is equal to 0. So if we set 1 minus 2x equal to 0, we would get 1 is equal to 2x, so therefore dividing by 2 gives us that x is 1/2. Okay. The y-intercept comes from plugging in 0 for x, so we're finding f of 0 here. So there we would find 1 minus 2 times 0 divided by 0, but for this particular one this is undefined, and that's because we have a vertical asymptote at 0. Okay, so there is no y-intercept. Let me make that a little bit better. So we'll just say there's none. Okay. Now, does a graph cross the horizontal asymptote? Well, in this case, it's not, because our horizontal asymptote is, negative 2, but we can look at that and figure it out. We'd have 1 minus 2x is equal, 1 minus 2x over x. We're trying to find out, does that ever have the y value of negative 2? If it does, then it means that it will cross the horizontal asymptote. Now remember, horizontal asymptote is a behavior as we approach infinity or negative infinity. So a graph could actually cross the horizontal asymptote, but it's going to come back to that horizontal asymptote as we extend indefinitely in either direction. So if we solve this equation, we would cross multiply to get 1 minus 2x is equal to negative 2x, but those negative 2x's, when we add them to both sides, give us 0, so we really have a contradiction, which means that our graph will never cross the horizontal asymptote. Now, I actually have in step 7 to graph, but let's go ahead and graph the pieces that we have here, and then we'll figure out a few additional points that we might need. So we're going to look at, we have a vertical asymptote at x is equal to 0. So let me choose this here, and I'm going to customize it to have green. Okay, so we have a vertical asymptote at x equals 0. Then we have a horizontal asymptote at x equals, or y equals negative 2 rather. So there is that information. Then we want to plot our 0, which is at 1/2. We don't have a y-intercept, and we know our graph will never cross the horizontal asymptote. Now another thing, your graph can never ever cross the vertical asymptote because of that value. Our function is undefined. So then we need a few other points. Well, we kind of know what's going to happen over here to the right and above the horizontal asymptote because we have a point at 1/2, 0. We know we can never cross this vertical asymptote, and we also know we're never going to cross the horizontal asymptote. So that graph is going to be asymptotic to both axes, or, well, I shouldn't say axes. We're going to be asymptotic to the y-axis, and we're going to approach this line y equals -2. If you wanted another point in that region, you could certainly enter like values of 1, 2, 3, or so on into the function and get a more precise graph if you want. But we know that the graph is going to look somewhat like this in this region. Now we don't know what's happening to the left of the vertical asymptote. So this is where you might want to enter a few values for x. So if we say x to be -1, so let's find f of -1. We would have 1 minus 2 times -1 divided by a -1, which is what? 1 plus 2, or 3 over -1, which will be -3. So we know at -1, -3, we have another point on our graph. Well, that's enough information to tell us the shape of the graph because we know we can't cross the vertical asymptote, nor can we cross the horizontal asymptote. So in this region, the graph is going to look like this. Okay. Now, what about our domain and range? The domain comes from excluding the values that make the denominator 0, so our domain of this function would be from -infinity to 0, union 0 to infinity, because the only restriction there is x equals 0. And what about our range? Our range is everything except for the horizontal asymptote because we can never take on that value. So we exclude everything, or include everything but the value of -2. So that would be -infinity to -2, union -2 to infinity. Okay. Now let me do one more example of this type and we'll conclude this video lesson. So now we want to graph the function 2x over x squared plus x minus 2. We're going to start in much the same way. We're going to find the vertical asymptotes. So the vertical asymptotes come from where the denominator is equal to 0. Well, if we set x squared plus x minus 2 equal to 0, we're going to need to factor that. And when we factor that, we get the factors x plus 2 times x minus 1 is equal to 0. So we have vertical asymptotes at x is equal to -2 and x is equal to 1. Again, I know they're vertical asymptotes there because x plus 2 and x minus 1 are not factors of the numerator, so we do not have something that reduces out. So we have vertical asymptotes at -2 and 1, and I'll go ahead and put those on the graph. Again, let me try to be color-coded here. So we have one at -2. Oops. And then one at 1. Okay. Now, what about our horizontal asymptote? Horizontal asymptote comes from the relationship of the degrees. The degree of the numerator is 1, the degree of the denominator is 2. And if you recall, when the degree of the denominator is larger than the numerator's degree, the horizontal asymptote is always y is equal to 0. Okay. So we can put that on our graph as well. Now, the zeros of our function are what? From where the numerator is equal to 0. So we're going to set 2x equal to 0 and solve, which gives us x is equal to 0. So we have an x-intercept at 0. And our y-intercept is also going to be that, right? Because if we have a x-intercept at 0, 0, the y-intercept is also crossing the y-axis there. But we could check that if we confirm by plugging in 0 for x. We'd have 2 times 0 over 0 squared plus 0 minus 2, which is 0 over negative 2 or 0. Now, does a graph cross the horizontal asymptote? Well, we can actually see from here, yes it does, but if you wanted to find that precisely, you would have to set our function f of x equal to the horizontal asymptote, which is 0. So if we set 2x over x squared plus x minus 2 equal to the horizontal asymptote of 0, we could cross multiply to get 2x equals 0. So x is 0. So we know it crosses the horizontal asymptote at 0. Now, we definitely need to find a few other points because we don't know what it's doing to the left and right of these asymptotes necessarily. And so to find a few other points, we're going to plug in something to the left of each of the vertical asymptotes. So we would plug in maybe negative 3, right, because our vertical asymptote here is at negative 2. So let's come down here and do that. If we want to plug in f of negative 3, we would have 2 times negative 3, which is negative 6. Negative 3 squared is 9, plus a negative 3 is 6, minus 2, which is 4. So we would have a negative 3 halves for that y value at negative 3. So negative 3, negative 3 halves. Okay. And that gives us enough information to draw the graph where it is asymptotic to these two asymptotes that we have. We know that the graph will not cross the vertical asymptote, so it can't extend to the right, and we know it's not going to cross the horizontal asymptote in this region because the only place it crosses is at 0. Now we need to figure out what's happening to the graph between negative 2 and 0, so let's plug in maybe negative 1. So if I plug in negative 1, I would have 2 times negative 1 is negative 2, and the denominator negative 1 squared is 1, plus a negative 1 is actually 0 minus 2. So we would have negative 2 over negative 2, which is 1. So we have another point on our graph at negative 1, 1. Now we need to figure out what's happening between 0 and 1. So if we plug in 1/2, okay, bear with me here. As we plug in 1/2, 2 times 1/2 is 1. Then we have 1/2 squared, which is 1/4, plus 1/2 minus 2. So when we simplify that expression, 1/4 plus 1/2 is, what, 3/4 minus 2. Well, 2 is 8/4, so 3/4 minus 8/4 would be a negative 5/4. When we divide that, we would multiply by the reciprocal to get negative 4/5. So at 1/2, our y value is negative 4/5. So now we know what the graph is going to look like between those two vertical asymptotes. It's going to extend upward because remember, to be a vertical asymptote, it has to approach it as we get closer and closer to it. And so there we go. That is the graph. Now, what about to the right of this asymptote? So to the right of x equals 1, let's plug in maybe 2. So if we plug in 2, f of 2 would equal 2 times 2 is 4. 2 squared is 4 plus 2 is 6 minus 2 is 4. So we'd have 4 over 4 or 1. So at 2 we have a y value of 1, which again is enough to tell us what the graph looks like there. It is going to all be above that horizontal asymptote and to the right of the vertical asymptote. So it's going to look like this. Now, what about the domain and range? The domain includes all values of x except for where we have vertical asymptotes. So the domain of this function is from negative infinity to negative 2, union negative 2 to 1, union 1 to infinity. Now the range, you might think we need to exclude 0 because that's the horizontal asymptote, but actually we take on that value, we cross the horizontal asymptote, so we do not have to exclude that value now. And we can tell from the middle piece that our range is going to be all real numbers. So the range is from negative infinity to infinity. Okay, now I want to show you real quickly how we might use the graphing calculator to get the graph of these functions. I've entered the two problems that I've illustrated for you here on the video into the graphing calculator in y equals. Notice that I had to put parentheses around the numerator and denominator unless it was just a simple variable or a single number. You really want to get in the habit of doing that. Some hints for you about graphing rational functions, because your calculator can make them look very weird. I've actually put my calculator in the dot mode. So if you press mode and arrow down to connected and go over to the right to dot and press enter, you'll be in the dot mode. So now whenever I graph, it's not going to try to connect those two endpoints where the asymptote actually should be. So let's press graph, and I'm in the standard viewing window right now. So I can see that I do have a horizontal asymptote and I also have a vertical asymptote. So you can see that it's getting dotted there. That's because it's getting so close, but it can't really fine-tune what the graph looks like. This is where you're really kind of smarter than the calculator, knowing where those asymptotes occur. So we can see the picture that resembles what we did earlier. And now if I go back to y equals, and I'm going to turn on my other equation that I've entered and turn off the top one, and now press graph, I can see the three regions that I have. Another hint for graphing rational functions is I like to use the z-decimal mode. So if you press zoom and 4, the z-decimal mode actually prevents you from having to put the calculator in the dot mode. It will give a good graph of a function that's in connected mode as well, but this is the way it looks. So it kind of lets you zero in on those pictures of the graph around the asymptotes a little bit better. Okay, so if you have any questions on how to graph with a horizontal asymptote, a vertical asymptote, finding the zeros and y-intercept and all of those key points, please contact me.